Okay, let me read it. There is a signal, x of t is equal to cosine 50 pi t. It's a periodic signal and it is certainly band limited. We all know the Fourier transform, what the Fourier transform of this thing looks like, right? It has two impulses at the corresponding frequencies and minus of that. In the first part, I'm asking you to determine the Nyquist frequency for the non-Alias sampling, which was the last thing that we have seen, if you remember. So you have to remember what the Nyquist frequency was. And in the last hour, I also briefly mentioned about the second part. Determine the minimum frequency for sampling this signal, of course, such that the signal can be perfectly reconstructed. The digital to analog conversion would be perfect. What is that minimum sampling frequency? If you think that that's the same as the Nyquist frequency in part A, then just write it down that way. If you can find a smaller sampling frequency, then indicate that one as well. Okay, I'm giving you like 2 minutes. In fact, 1.5 minutes, because this doesn't require any calculation. It's just by inspection you say that it's this, this is that. From here, what you need to do in order to determine the answer to part A, the Nyquist frequency. The Nyquist frequency is what? It's twice the maximum frequency. There is only one frequency here. It doesn't have a maximum frequency. There's a single frequency anyway. If you draw the Fourier transform of this thing, this is what you will see. Two impulses with magnitudes 1/2 and 1/2 each at 50 pi and minus 50 pi. Since the maximum frequency is 50 pi, the Nyquist frequency for non-Alias sampling is omega s is equal to twice of this, and that is 100 pi simply. The other part is the interesting one here. This Nyquist frequency is necessary to make sure that nothing is overlapping after sampling. If your signal is considered to be a full band signal between minus 50 pi and plus 50 pi. So if there are a lot of things in between, then in order to separate or completely isolate them in the replicas of these two impulses towards the right and towards the left, you need to use this sampling frequency and put a center here at 100 pi, for example, and integer multiples of that, and replicate. Let me use this green, but it looks bright anyway. These two impulses like this, for instance. It must be marginally or slightly larger than 100 pi, of course, because otherwise these two impulses will completely overlap. We don't want that. So let's indicate it like this, for example. 100 pi plus epsilon sort of thing. But it doesn't matter. You could equally say 100 pi. That's the correct answer. But this is quite unnecessary because, as you see, these impulses will not mix to each other even if you use some lower frequencies, like these two impulses are here. And if I replicate at, this is 50, sorry, let me write it with white. This is 50 pi. If I use another frequency here, which is 50 pi plus epsilon, something like this, and then repeat these two impulses towards the right, what will they look like? They will be like these two impulses, green impulses. And further repeating to the right at twice this 50 pi plus epsilon thing, it will be like this. And if you go again to the right, so this will be 100 pi. If you go 150 pi here, the replica will be something like this. Oops, sorry. Something like this perhaps. So as you see, they don't even overlap with each other. And if you go to the left hand side, they won't occlude each other either. So they don't match like this. It is a very nice exercise to try to think of something even smaller than 50 pi. Will that be possible? And the answer is yes, still. But for example, if you use like 50 pi or something like this, then the problem may be this. You may ask this question. Then how are we going to recover from this discrete time, or it's not discrete time, but sampled spectrum, starting from the sampled spectrum, how can we recover our original signal? The way to recover the original signal, as long as they are not occluded, is just by deliberately choosing a band pass filter. For example, you can choose a band pass filter, a very narrow one, like this. A very narrow band pass filter, and it is only picking this impulse and this impulse. It's not a low pass filter, it's not taking everything in between. It's only taking this impulse and this impulse. So it's a very deliberately chosen band pass filter. Using that band pass filter, you have these two impulses, which really corresponds to our original signal anyway. So if it's not impulses like this, if they contain some band-limited band pass signals here and here, what you really need to do is to design a replica pattern so that those replicas will not coincide on top of each other. That's the only constraint. And then the reconstruction is quite simply by applying a band pass filter right at the band limits of our original signal. Just pick those positions only, band pass positions, by band pass filtering. That's what you can do. Okay? Be careful about that. I truly tend to ask a question like that in the final, for example. Now, apart from this concept, there is one final thing that we have to consider, and that is the discrete time axis conversion. We haven't completed the discretization process yet. We sampled our signal by multiplying with an impulse train. This spectrum corresponds to that, or this one corresponds to that. But it doesn't correspond to discrete time signal yet. For the discrete time conversion, however, the situation is not very complicated if you follow carefully. For example, this is our original signal spectrum, x of j omega on the omega axis. It has some band limits from minus omega c to omega c. It must be band limited, otherwise you cannot sample it anyway. By multiplying with an impulse train, what we get will be replicas of this thing. One of them will be itself from minus omega c to omega c, and the others will be replicas where what is the center of the other replica? It's the sampling frequency, omega s, or 2 pi over capital T, this thing. And here it is twice of that. And it goes on to the left and to the right like this. Like this. This is, let's say, x sampled of j omega. And it is not the discrete time version of our signal. What you have to do is, you have to draw your new spectrum of xd, let's call it, of e to the j omega, which is the discrete time Fourier transform of our discretized signal of this. What does it look like? It must look like this, by the way. But it must also satisfy one very important property that I am constantly repeating again and again. And what is that? This thing must be 2 pi periodic, because it's the Fourier transform of a discrete time signal. It's a discrete time Fourier transform. So it is 2 pi periodic. Is this signal periodic? Yes, it is, but it's not 2 pi periodic. That's the only difference. By the way, this omega s, let me write it to be equal to 2 pi over capital T. It's not 2 pi periodic, it is 2 pi over capital T periodic. So how are we going to convert this one to this one? Simple, we will just scale the axis. This, let's call it omega prime, new omega prime axis is, so we have to put it like xd of e to the j omega prime, because it's a new frequency parameter. It's not the same frequency as the continuous signals frequency. Okay, this is different. So this new omega prime will be equal to capital T times omega. We are just scaling this axis. Or it's even easier than that to interpret. It's the same shape. We're not really changing the shape. It's the same. We are all only making one single change, which is this point. We're not going to say it omega s anymore. We are going to call it 2 pi. And that's it. Okay, it's the same shape. It's just a scaling of the frequency axis. And how did we have this kind of shape? By multiplying this old axis at the top figure by capital T. So this is 2 pi, this is 4 pi, and this is again 0, and this is minus 2 pi, it becomes. Of course, some of the parameters also change. For example, previously it was omega c. Now what is it? What is it? Capital T times. Yeah. Omega c times capital T, as simple as that. And this point is, of course, 2 pi minus capital T times omega c. That's the point. So the shape is the same. And this corresponds to discrete time converted signals Fourier transform. And that's it, you are finished. You're not expected to do anything more than that. Okay? Previously, in the previous week, we came from here to here. Now, the last step is to go from here to here, which is nothing. It's the same shape. You're just renaming the axis to be not to be equal to omega s, but you're now calling it 2 pi, and that's it. That's the discrete time Fourier transform. Now, using that discrete time Fourier transform, an important thing that you can do is, of course, nowadays, it's not even nowadays, for the last, I don't know, 3 decades or something, people just do digital signal processing. Digital signal processing is nothing but discrete time processing of signals. But in real life, some of the signals are continuous time signals. So how are we going to process them? And that is called the discrete time processing of continuous time signals. And how are you going to process them using a computer? Suppose your speech, you're talking, that's a continuous time signal. You have a microphone. Somehow you need to sample them first, and then you have to process them using the computer. But at the end, you have to make digital to analog conversion again and obtain something analog and feed them to the speakers, loudspeakers, and you listen to them. In between, something is going on. So what is that? That is your continuous time signal being multiplied by an impulse train, which we denote by P of t, as we did last week. This is convert to discrete time, and what you have here is this xd of n, whose Fourier transform, discrete time Fourier transform, is this one. So you have now this xd of n. Now in between you can do just anything. It may be easier for us to think of linear and time invariant systems which has an impulse response and therefore the spectral response like this. But it could be quite nonlinear as well, because you have a computer now, and using the computer it's not very difficult to design nonlinear effects and nonlinear filters. You can take the squares of the samples, for example. So whatever, this is the computer. And then you have yd of n, the processed signal. You have to convert them to continuous time impulse train. Okay? That's like the difference between this one, which is, let's call xp of t, and this one, xd of n. From xd of n, you have to convert back to xp of t. So the output of this one is yp of t, which is continuous time, but it consists of impulses. These were discrete time samples, like a vector here, but these are impulses. The separation between these samples are 1, like this. The separation, so this is 0, 1, 2, 3. But this signal consists of real continuous time impulses, this yp of t, and the separation between them are capital T. So for this conversion, you need to know the sampling frequency or the sampling period. And then from here, what you do is a low-pass filter whose cutoff frequencies are the Nyquist frequencies. So the quiz question is not valid here. Okay, I'm not doing a band-pass filtering or anything. It's just normal, regular low-pass filtering at the Nyquist rate, and the output is y of t. Now, that's a long diagram. But whatever that diagram is, this large thing, is a transfer function from xc of t to y of t. So it is equivalent to xc of t going into a system, and I'm again assuming a linear and time invariant system if this is a linear and time invariant discrete time system, and the output is y of t. All right, so an engineering problem here is usually from normal calculations of signals and systems you can design this one. For example, it may correspond to a filtering, a low-pass filtering, band-pass filtering, any kind of a filter that you design. But you cannot implement that filter using capacitors, inductors, and resistors, or even transistors, whatever you may have, in the analog domain. Analog filter design is a headache. Okay, it's difficult. But your computers are quite capable. You can just do anything. Even if you don't use any programming, you can use MATLAB, for example, which has a lot of filters inside. So MATLAB is here. How can you use that? What is the equivalent HD corresponding to the effect, the original effect of h of j omega? That is possible. It is possible to do it, or it's always possible to find an HD of e to the j omega if your original continuous time signal is band limited. For instance, let's assume that your h of j omega is equal to j omega. This is an example. What is that? What is this system? It's a differentiator. If you multiply the Fourier transform by j omega, in the time domain, it corresponds to taking the derivative of your time signal. Okay? You remember that? So this system is taking the derivative. Now clearly, the system transfer function is complex, and it's not possible to plot something complex. So instead of that, I'm plotting the magnitude of it for the time being, just for illustration purposes, which looks like this. You remember this, okay? This is the frequency axis. Now your signal, the input signal xc of t, with which we are going to use this filter, it must be band limited. Otherwise you cannot sample it. Okay? You can safely assume that it has some band limit. For example, from here to here, it is band limited. Something like this, I don't know, whatever. And this is your signal. Okay? Now, when you apply this filter to this signal in the Fourier domain, what you need to do is you have to multiply them, right? We multiply in the spectrum axis, in the frequency axis. So in the multiplication, you see that this top system here, this one, which is j omega, the values of that filter is irrelevant if the frequencies are beyond omega c. Sorry. So these points are not related to whatever we have. We are not interested in those places because the signal does not apply to those frequencies. They are independent. They are irrelevant, completely irrelevant. So, for example, what I can do is, let's not think of this h of j omega, but a new one. And I'm going to call it hp of j omega. Of course, the name has a meaning, but it happens to be like this. Up to omega c, and of course, minus omega c. It has the same shape. The same shape as that one. But after that, we're not interested because the signal is band limited within this range only. So what I'm going to do is, I'm going to repeat this pattern. This one is twice omega c, and this is minus 2 omega c, like this. And it is going on. I'm periodically repeating this central pattern, in other words. Now, what does this correspond to? It corresponds to a discrete time version of the original continuous time signal. It is like the sampled system. I'm sampling the system now. And in order to make it a completely discrete time system, I'm going to call this repetition points, which was previous to 2 omega c, to be equal to 2 pi. So, sorry, it's not omega c here. Omega c, twice omega c is here. I'm sorry about that. This is minus 2 omega c. And this is 3 omega c. And this is minus 3 omega c. Sorry about the confusion, because I'm usually expecting the triangles to be in the center. It's not a triangle in the center, it's a V shape. Sorry about the confusion. So this is the correct legends. And so 2 pi is somewhere here. Let's draw it like this. And we have this V shape repeating like this. And this new system is HD of e to the j omega. Okay? Of course, this omega c point will be capital T times omega c. The new point will not be omega c anymore, because we are scaling this frequency axis by capital T to get to this point. So what you do is you have to assign this pulse to have a sampling period of capital T first of all. And if you use, after this choice of sampling period, then we can apply this instead of this discrete time HD filter. Instead of this one, you apply this filter. This is HD of e to the j omega, whose magnitude is given here. And then, after applying that, you get an output. From this output, you convert the output to continuous pulses separated by capital T, continuous impulses, and apply a low-pass filter, and the output will be what? The output will be the derivative of the time signal corresponding to this. Of course, there is a time signal corresponding to that. And the output will be the derivative of it. And what did I do? I didn't apply a derivative filter. This large system, overall large system, corresponds to a derivative filter, but I didn't apply a differentiator. Instead, I sampled it, applied a discrete time system, and that system has a frequency response like this, and then converted back to analog, and the output here, y of t, is the derivative of xc of t. I processed using the computer. I processed the continuous time system using a computer. What did I do? I sampled or converted everything to a discrete time version in the filter domain. I sampled the filter, in other words. This is the filter, the system, and this one is the sampled system. That's what I did. Now the question that you have to ask yourselves is the following. If I give you a different shape here, will you be able to construct the sampled version of that system? And the answer must be, of course, yes. What you have to do is you have to cut from the cutoff frequencies, take only the central portion, and then repeat them. That's it. That is your system, discrete time system, for processing continuous time signals after sampling. Is that clear? Because, of course, again, there will be a question like this. I'm not going to give you this derivative system anymore because I have already given you. It will be another shape, any shape. It doesn't matter what shape it is. You have to just replicate the central portion of it and apply and say that this is your discrete time system that you have to apply in this framework here. This is the discrete time system. So that's the last thing that I would like to mention about in terms of sampling business. Now we are going to start a new chapter. As I say, the sampling chapter would be covered very briefly because there is a whole course dedicated to sampling and sampled signal processing, which is called digital signal processing. So this gives you a glimpse of what may be going on over there. However, our new topic is more important than that, and that is the Laplace transform. Let me immediately give you the Laplace transform definition because we are quite familiar with Laplace transforms, I guess, from differential equations. That is the notation of S that we have here, and that is, the definition is from minus infinity to infinity ht e to the minus st dt. it truly resembles the Fourier transform. What was the Fourier transform? It was h of j omega is equal to integral from minus infinity to infinity ht e to the minus j omega t dt. So what's the substitution here? The substitution is from j omega to s. If you call it this way, what you get will be the Laplace transform. But it's a bit more than that. This Laplace transform is a superset of the Fourier transform. It includes the Fourier transform only for s is equal to j omega. That will be equal to h of j omega, the Fourier transform. But it is more than that. In general, S is not only purely imaginary j omega, but it may also have a real part, usually indicated by a sigma plus j omega. So the Fourier transform is the Laplace transform for sigma is equal to 0 case, the real part. Now, if you take a look at e to the st, this signal, then this signal is equal to e to the sigma plus j omega t, isn't it? Which is also equal to e to the sigma t, e to the j omega t. So the complex exponential here becomes partly real exponential and partly complex exponential. This complex exponential is a sinusoid. It has a pure oscillation consisting of cosine and sines. But this one is a real exponential, and depending on the value of sigma, it may be a decaying exponential or an increasing exponential. For example, in one case, the case for the decaying exponential, this overall shape will be, except for the complex issues, will be something like this. It has an envelope. This envelope is the real exponential. I'm assuming sigma is less than 1 in magnitude, and there is an oscillation. Okay, so this decay constant is sigma, and the period from here to here is capital T, where omega is equal to 2 pi over capital T, this omega. So the frequency of these oscillations is determined by omega, and the decay factor is determined by this sigma. Now, what do we gain by assigning such a coefficient of s instead of j omega? What was wrong with j omega? The problem about j omega is, first of all, it is a little bit, it takes longer to write. So it's more practical to put an s in the transfer functions. Wherever you have omega, just replace them with s. It will be more compact for the representation. But of course, it's an unimportant consequence. The more important consequence is that in some cases, if the signal is not suitable for the Fourier transform, if it violates the Dirichlet conditions, in other words. Even if they may violate the Dirichlet conditions, by properly choosing a sigma and by suppressing your signal, it is still possible to obtain the Laplace transform. So Laplace transform exists for a lot more signals than the Fourier transform. Of course, these things will be clearer if we start seeing examples. And when we see examples, you will see that the transformation and the inverse transformation will be much easier. By the way, let me put a very quick and important reminder. This Laplace transform is probably not the Laplace transform that you have been using in differential equations, because that Laplace transform usually starts from 0 in the expression. This is from minus infinity to infinity. That's a difference, and that difference will be like this. In the differential equations, again, you have initial conditions, right? There are initial conditions. That initial condition is necessary if you start from 0, because you don't know what happened before 0. There is a starting point, and therefore you need an initial condition. That's a different way of attacking the same problem. Here it will be easier for us. We will not have any initial conditions. It will be from minus infinity to infinity. This is a two-sided Laplace transform, they call. That's what they say. Or bilateral, two-sided. The other Laplace transform that you have been using in differential equations is unilateral or single-sided Laplace transform from 0 to infinity, where you need initial conditions. I believe that the solution of problems with initial conditions is a little bit more difficult than this one. These are easy. Let's see this example, which is the trivial case, e to the minus at u of t. What is the Laplace transform of this one? That is x of s is equal to, from minus infinity to infinity, x of t, which is e to the minus at u of t, e to the minus st dt. Because of this u of t, this integral may now start from 0. From 0 to infinity, e to the, in minus parentheses, a plus s t dt. Do you all follow this step? I combined these exponentials in a single term, and I dropped this u of t because it forces the signal to start from 0. So I changed the integration to start from 0 to go to infinity. So this is my integral, new integral. And that is equal to what? Yeah. There's a minus 1 over a plus s. And e to the minus a plus s t from infinity to 0. At infinity, we want this exponential term to be 0, because it is either 0 or infinity. If the exponent is growing, then it will be infinity. If it is decaying, it goes down to 0. Let's assume that it goes down to 0. We will see why or when it goes down to 0, by the way. Then it will be 0 minus another minus 1 over a plus s, and with t is equal to 0, e to the minus something times 0 is e to the 0, which is 1. So I'll close the parentheses. And that makes 1 over a plus s. By the way, if you take a look at your notes, you will see that the Fourier transform of that was already 1 over a plus j omega, wasn't that? So it's the same idea. But in the Fourier transform expression, what did we say about the value of a for the Fourier transform? It must be a positive number, right? It cannot be a negative number. If it is a negative number, then e to the minus will be a plus. E to the plus something times t is a growing exponential, and it immediately violates the Dirichlet conditions, and the Fourier transform doesn't exist, right? That's okay. But even if it is negative, now is it possible to have a Laplace transform? And that is the most critical point here. This may be negative, and still the Laplace transform exists. The only thing that is that this must be decaying. And how can we guarantee that it decays? It decays as long as a plus s, the real part of it, the real part of a plus s is positive. Then e to the minus that thing will be a negative exponential, and the real part will decay. Without this real part, expression, it makes no sense because this S has an imaginary part and the real part, and the imaginary part only causes oscillation. It doesn't cause an increase or a decrease in the decay. Okay? So the real part of A plus S must be greater than 0. The real part of A is A. The real part of S is sigma. Must be greater than 0. And that means sigma must be greater than minus A. That's it. That's a condition. But that condition can be satisfied. Sigma is an arbitrary parameter that can be chosen by us. We will choose what sigma is. So we have to choose the sigma of this S parameter such that it is greater than minus A. Under any circumstances, it must be satisfied. If A is a positive number, if A is a positive number, then this already decays. E to the minus AT will be a decaying exponential. Then the Fourier transform exists, right? If that is a positive number, then minus A will be a negative number. So sigma is greater than a negative number. For example, sigma is greater than minus 3. So the example is A is equal to 3. So sigma is greater than minus 3. You must choose sigma to be greater than minus 3. No big deal. That's what you can say. You just say that sigma is greater than minus 3 is your condition for the existence of Laplace transform. By the way, does it satisfy the Fourier conditions? Can you see the relation to Fourier transform? What was the Fourier transform in terms of Laplace? Fourier transform is the Laplace transform at S is equal to j omega, which means, sigma is equal to 0, it means. So, sigma is greater than minus 3. Is sigma is equal to 0 greater than minus 3? Yes, it is. So, you immediately see that since sigma is equal to 0 is in your condition limits, then the Fourier transform exists. But it could be another signal where A is equal to, let's call, minus 4. If A is equal to minus 4, then this will be e to the 4t u of t, which is a very fast growing exponential, and the Fourier transform doesn't exist. Can we see it from there? If A is equal to minus 4, then sigma must be greater than 4. So it must be greater than 4, therefore 0 is not satisfied in this condition. And immediately we see that since sigma is equal to 0 is not in your condition limits, the Fourier transform doesn't exist. Now, we have this to be Laplace transform, but without this condition on sigma, it is not complete. You have to always describe the condition on sigma as well. That's the only technical difference between Fourier transform and the Laplace transform. For the Laplace transform, if you guys give me an answer like h of s is equal to 1 over a plus s, out of 10 points you will get 5 points. I'm not saying you will get 9 points. Okay, you will get 5 points. You have to tell me the condition on sigma as well. That's a necessary condition, half as important as the Laplace transform itself. And there is a way to indicate that condition on sigma as well. Although I said that we use sigma as the real part, in the book you will see that the notation is like this. They say real part of S is greater than A, minus A for this example. So don't use sigma. Say that real part of S is like this. That is also known as the region of convergence. In this region of the real part, your Laplace transform integral, which was this, this integral converges. Otherwise, if the real part of S is not greater than minus a, again only for I'm talking about this example, if it's not like that, then the integral will not converge, it will be infinity, it will be a divergent integral. Okay? So this is called region of convergence and abbreviated as ROC, region of convergence. Now before going to the break and going with the other examples, the region of convergence, there's a name as you see, region. That region must be indicated on the so-called S-plane. So I'm drawing now the S-plane. What we mean by that? This, the horizontal axis is the real axis of S, and the vertical is the imaginary axis. So for example, when I put an S here, or let's put it here, an S, what does it mean? It means that this is sigma, the real part, and this is omega, the imaginary part, j omega in other words, right? So this is the j omega axis in other words, and this is the real axis. Now let me briefly erase this and think of this real part of S is greater than minus a. So, again, suppose a is equal to 3, then minus a is some point here, minus 3. Okay, and we said that real part is greater than minus a. How are we going to draw it? It is only related with the real part, and the imaginary part is independent from that. We didn't put any constraints on the imaginary part, so that will be a vertical limit boundary, and since it is greater than that, it is to the right hand side of that boundary. And this starting from minus 3 going all the way to plus infinity is the region of convergence. Now you have two notations, therefore, two ways to notate the answer. The first part of the answer is h of s is equal to 1 over a plus s, and the region of convergence is either written like this or drawn like this, whichever I may ask. Sometimes I ask you to draw the region of convergence, and when I say that, don't forget to draw a figure like this and indicate the region of convergence. Or if I don't ask you to indicate the graphic, then you can just give me this answer as well. They are equal. By the way, do you understand why this is dashed? Not a solid line. Yeah, it's not included. There is no equality. So this stripe or boundary is not included in the region of convergence. All the places except this line, it is strictly greater than minus a. Okay, that's why that's a dashed figure over there. We will see with other examples, and we will see the significance of why this region of convergence is so important in the next hour.